Good morning, everybody, or good afternoon, or good evening, wherever you may be, whatever it is. Welcome to week 13. We've got PLC 13 posted this week. I got homework 6 on special relativity rolling, and I'm going for a week on Wednesday for that one. So we'll finish off relativity today, probably tomorrow, so you'll have about a week's worth of time to look back on the stuff that we started last week and do this week. And I want to have a concept quiz on relativity on Thursday. So keep an eye out for that. That'll be up and rolling as usual with the quizzes all day Thursday. Other than that, I'd like to keep going with some special relativity and fill in a few more things of what we were talking about and push forward into a little bit more of the dynamic description. In other words, what happens to things like the energy and the mass and momentum and things like that. So if I remember, which I may or may not, but last time, which I saw you last, would have been last Wednesday, we were talking about a trip out and back and trying to deal with some of that stuff. So we talked about space-time diagrams, probably about as much as we're going to. I want to have a couple more examples for you to look at and do a couple of examples of drawing them so you can see how to do that. But in terms of interpretation, if you're presented with one, that should be all set. We've talked about the time being slower for moving clocks. I also want to fill in a few other things and then get back to the paradox of the twins. So in terms of special relativity so far, we've found that in terms of the coordinates on the space-time diagrams, those coordinates could be different for different observers. If you are in motion with respect to another observer and you're comparing coordinates, then what you might find is that your interpretation of where and when something happened will be different. And so one of the reasons for that we were exploring a little bit in the last class. Sorry, I just got to plug the computer in here. There we go. We were exploring in the last class such that we looked at the light beam bouncing in the train and we looked at the distance that the light had to travel. And the situation is when you consider the interval is t squared minus x squared, such that if you are moving in space, that causes you to take more time, right? So the differences in the times is like is almost like if you're not moving in space, then you're experiencing a certain amount of time. But if you're moving with respect to, say, me or something like that, right? And I look at your watch, I'm going to say, well, you're moving, which means you have to have taken a greater amount of time. So your time, well, anyway, so the times and the spaces are, the times and positions of things are different. So people will experience different times and different space coordinates. So we looked at the light beam bouncing in the train, and we came to the idea that if it's a clock that's moving with respect to you, then the time between the ticks is larger, which means that the number of ticks, this is as seen by someone stationary, or it's in a different reference frame, right? Moving clock will experience more time between their ticks as seen by someone else, and therefore fewer total ticks, which means that for the person who is observing this moving clock, they're seeing the moving clock running slower. Note that that does not mean in that reference frame the clock is running slower. It's not. This has to be a clock moving with respect to an observer. Now, if I look at my watch is never moving with respect to me because it's always right here. So my watch and my time will always be exactly what it, I don't know, supposed to be. Not quite the right word, but I won't detect any deviation in my flow of time. I might detect deviations in other people's flow of time, or they might detect deviations in mine, but I will never see any deviation in my own flow. My clock will never run slow because it's always in my reference frame. So in order to calculate the amount that time is slowed down, according to the person who's observing the moving clock, we introduce a new quantity. Time is slowed on a moving clock. Okay. We introduce a new quantity known as the gamma factor. You can think of it, this gamma factor, you can think of it as the ratio between the times that we are measuring. Okay, so for example, if I think of the amount of time that, if you think of the amount of time that passes on a clock that is stationary relative to you versus the amount of time passing on a moving clock, the moving clock's going to run slower, right? So you could almost ask, well, how much is it moving slower, right? It's so it's almost like you'd say, well, I'm gonna take the, if I want to say like the Earth clock, if I'm thinking of a situation like this, where I have an Earth, say, frame of reference here, and then we have a moving frame of reference that would be inclined like this. Then what we'd say is that the factor that links the two of these is the gamma factor, and it comes out of the hyperbolic geometry of how the space-time is different than Euclidean, which I've mentioned, but is not something we're going to really explore too much of. So the moving clock time is going to be less. You could imagine like dividing by the gamma factor, basically the time stretch factor. Okay. You can think of this as a time stretch factor, though it's going to also be apparent that this is also going to be a length factor. Okay. In other words, I'm going to find that a moving length is different than a regular length. So the Earth time here is greater than the moving time. This would be in, for example, the XT frame. And this could be, for example, on the rocket frame that's moving in the prime frame, something like that, right? So we on Earth would watch the rocket move by and say the clock is running slower. Our time is going to be more. And how much more? It's going to be more by gamma. Now, what is the gamma factor? Well, the gamma factor relates these two things, and it's only a function of the speed, the relative speed between the two objects. Okay. So without proof, I'll just tell you it's this, where I'm using our convention that c is equal to 1, so that v is a fraction of light speed. If you would prefer, you could certainly change this out and use the v over c fraction. It would be squared. You could use the v over c fraction for this right here instead of just v. But the idea is the same. Okay, either you're thinking of the speed as a literal fraction, or you're thinking of it as c equal to 1 and it's just some number less than 1. The same idea. So what we find is that when objects are in motion with respect to us, we also happen to find that their lengths are not what the person in the rest frame of the object would see. In other words, you can imagine, since I have a meter stick here, we measure this to be 1 meter long. But if I were to then throw this past, we would actually measure this to be less than 1 meter long. And so the question is, well, what's going on? So the issue here is the simultaneity of the measurements. In other words, I have to find the two ends of the meter stick simultaneously in order to take a length measurement that is considered to be good, or it's considered to be a reasonable length measurement of the object, right? I'd have to go to the two edges of the object and go, they're right here, and then all I have to do is measure between them. But if the object is moving past us like this, and you go, here's the front edge, and then here's the back edge, notice that it has moved in between my two measurements. Now, obviously, they were not simultaneous, right? It's very difficult to take simultaneous measurements of a moving object, and it's because of that time delay or you can imagine it's kind of because of that time delay that we can't take proper measurements of a moving object. So let me show you this. We'll get back to that thing in a sec. I want to talk a little bit about the simultaneity of objects. Of events. And I want to do this example for you of a moving train. Back to another train car example. Yep, I know. It's okay. We got a moving train here. This is a train car on rails. And we have two observers. One observer is directly in the center of the train car, such that halfway between, you say this is half of the length and that's half of the length. So this observer is directly in the middle of the train car. And they are passing by someone who is standing on Earth watching the train go by, right? The train's going by at some speed v with respect to this observer down here. At the instant that these two observers are lined up like this, lightning strikes the tracks right at the edge of the wheels, right there and right there. Okay, simultaneously according to the person here on Earth. They see the lightning strikes hitting right at the edges of the train car. Okay. So the question is, what does the person on the train see? All right. So let's first go back and say, what's the consequence of the lightning strikes hitting simultaneously for the Earth observer? Okay. So we'll say that the lightning strikes are simultaneous. for the Earth observer. That means that if I consider the light that is going from the lightning strike to the observer, you could kind of imagine it as wave fronts traveling, right? So it would be kind of like a wave front would be here and then would be here, right? And would travel outwards as if it had started right at this point, and it comes out like a point source radiating in a, well, what would be spherical, but for us is only going to be circular on the board. You can imagine that the wave fronts, if I only draw an arc of the wavefront, right, it might be like this, right? There's a wavefront going around, and then another one like this, and another one like that. Whereas this one's doing basically the exact same thing. And these two waves are hitting the observer at the same exact time. So the lightning is striking at the same time. That's like an omnipotent viewpoint, where we, as the Earth observers, are viewing the lightning strikes at the exact same time entering our eye. So we say here that the light is observed simultaneously, or the light is, seen simultaneously. By that observer. So the question is this, so the question was, what does this look like from the person on the train? So one of the byproducts of that is I want to ask, is the person on the train also going to view the lightning strikes, not the actual strikes themselves, but the light from the lightning strikes hitting the Earth observer at the same time? Okay, so note the question here. This person sees, in other words, light enters their eye, the light from these two strikes at the same time, and therefore can deduce, since they are halfway between the ends of the train car, that these lightning strikes must have happened simultaneously. Now I want to ask, according to the person on the train, first thing, are these two lights hitting the person here on Earth at the same time? Are these two wavefronts still hitting the person at the same time? So one way you could answer that is by taking the person out of it, okay? You can take the person away and instead make a machine. Make a machine which has two light detectors on either end and a little flag or something in the middle, such that if two light wavefronts, whatever, two lights enter the two light detectors at the exact same time, or within some, range, some tolerance of the detectors, then it sends a signal to the flag and it says, oh yep, I got these within the time frame that I'm supposed to. Raise the flag. Okay. So if the flag goes up, then we know that the strikes were observed simultaneously by the machine. Now, the question I would ask is, does everyone agree that the flag will go up? Or whatever it is that you decide, right? A little puff of smoke let out, or a siren goes off, whatever you like, a red light goes on. Does everyone agree that that happens? Or can you be in a reference frame such that the flag does not go up? I think that you'd agree that if the flag goes up, everybody sees the flag go up, right? It's not like you can be in a frame and be like, oh, no flag. No, the flag goes up. Either the flag goes up or it doesn't go up, and everybody has to agree on that. That is, in other words, an event in space-time that everyone agrees on. So what that means is, when we go to drawing this on a space-time diagram, that means there's a point here and everybody agrees, oh, yep, that happened, right? So One of the reasons I'm going through this is because of the word simultaneous. I've made a big deal about simultaneous events not necessarily being simultaneous for everyone. Yet, here I am saying there's a simultaneous thing happening, but now everyone's agreeing on it. Yes, but this is different. This is not two events happening separated in space, right? This is basically one event happening at the same point in space at the same time. Now, do we agree on the time and the space? No. But we agreed that this thing happened at some place in space and time. In other words, we might disagree on what the coordinates of this point are, but we will agree that the point is there. In other words, these two lightning bolts, the wavefronts from the lightning bolts hit this person at the same time because it happened right there. It's not two different distinct things happening at different times or same time. It's one thing happening right here at the same time, and everyone will agree on that. So the light is seen simultaneously by the observer, and so what that means is everyone agrees that the light was seen simultaneously by this person. That is what this person is going to agree on. Now, the question is, if the train car is moving, what does the person on the train see? Well, the person on the train is going to see the person on Earth going this way, right? So if the person on Earth is going this way, that means they started over here and they're moving this way. They eventually get here, at which point the lightning strikes hit them simultaneously. And then they keep moving. So what does that mean? That means that according to the person on the train, if the person on Earth started back here and was moving this way, in order for this person to see both lightning strikes at the same time, what had to have happened? Can you see that since there's a time delay in the lightning strike happening and then the wave of light propagating to get to the person, we are going to need to have this lightning bolt happen first in the frame of the person in the train. Can you see that? Reason being that if the person on Earth is moving this way according to the person on the train, then the lightning bolt strikes and the light is now trying to catch up to the person, whereas this lightning bolt strikes and this light is on the way to hit the person. This one had to catch up since it took extra time to catch the person, whereas the person ran into the one from this side over here on the left. The one on the right must have happened first, or if you like, the one in the front. That lightning bolt had to have happened first according to the person on the train. Notice what has happened now, right? The person on the train will notice that this lightning bolt went first and chased this person down, whereas now, as this person's approaching the center point, this one then goes off and the light comes and hits at the exact time that this one catches up from the front side, like that. This causes the person on the train to tell the person on the ground, you cannot have made a proper measurement of my train, because the lightning bolts weren't simultaneous. You didn't take the two ends of the train, boom, here it is, right? The person on the ground maybe thinks they did, but they couldn't have, because the person on the train sees lightning strike here, then the person moves, and then this lightning strike happens. So there's no way that they can get a proper length measurement of the train. What does this look like on a space-time diagram? Well, if I put the train in here, let's put the train, say, here, like so at t prime, and let's do the x prime axes. Wow, this is going to be pretty crazy. Here's the x prime axis, all right? Actually, let's do this, even better. Let's call this, well, darn, I kind of didn't really want to put that there, but okay, let's do this. Let's call that the rear end of the train, the back end here on the left. Let's call this set axis what the back end of the train is doing. And let's call this one over here. Let me take this off just so I can see this a little better. We'll do that later. And over here is the front end of it. So 1, 2, 3, 1, 2, 3 here. 1, 2. Whoops, like this. All right. So this will be the back of the train. This will be the front of the train. Right? This is also a T prime axis. And the person, right, is directly halfway in between. All right, so the lightning strikes are happening, for example, if they happen simultaneously from the Earth observer's point of view, which was what we said, then suppose that they happen directly along the x-axis here. That means that I go at a 45-degree angle, and I say, all right, that's the light from that lightning strike going this way. Here's light from this lightning strike going this way. Yep. And they hit right there. Okay, remember we set it up such that light was C was equal to 1, such that that meant that light travels on the 45-degree lines for these space-time diagrams. So if the lightning strikes happen at, say, t equals 0 for the Earth observer, then the light is emitted from each of the front and back of the train at the same time, and the light goes the same distance and reaches the observer at the same time, right? So that means the observer on Earth has a line that looks like this. Right, like that. That's, well, I don't know if T is the right one to put there because I've got a whole bunch of T axes, but this is the observer. This is the Earth observer. And it's known as the world line. In other words, this tells us what they've been doing. They've not been moving according to, in the Earth frame, right? According to them. All right, so now look at what happens if you look at it in the train perspective. And I had better get a different color for this because I need to put that x prime axis back in here, which was here. Okay, like this. If I say the x prime axis is there, whoops, if the x prime axis is, where did I have it? There. Okay, this is the x prime axis. Then I measure simultaneity for the train as anything parallel with that, which means that at t being 0, well, that's the Earth observer's frame. That's when this Earth observer saw both of the lightning strikes happen. At t prime equals 0, this lightning strike definitely happens, but notice, when was the other one? It was back here, which means it happened before t prime equals 0. Some people get kind of unhappy about the idea that it's negative time, but really it's just time prior to you clicking your watch to be 0 or noon or on a clock or something like that. Right? It's just time before we said it was 0. So according to the person on the train, these two events are not simultaneous because that one happened well after this one had happened. Does that make sense? T prime being 0 is at the top x prime line here. This happens before then. At some time later, this one happens, And that's when the light hits the observer on the Earth at the exact same time. All right. So that's what this situation looks like on a space-time diagram. Remember, when you are drawing light on a space-time diagram, it always goes along the 45-degree angle. That's why we have set all of this up in the way we did. All right. So again, two things happening. Number one, the events are not simultaneous. And notice that I am now talking about two things that happen separated in space. Right? These two lightning strikes are separated in space. According to one person, they happened at the same time, but according to the other person, they didn't. That's what simultaneity means. These two lightning strikes hitting this person at the same time is not in question because it happened at the exact same point in space, right? These two things came and coalesced at that point right there at the same time, so everybody agrees on that. All right, so that's the difference between loss of simultaneousness, simultaneity, and what happens when something, when the situation like this happens where you have light hitting someone simultaneously. All right. Okay, the other part to this is that they will not agree on the length of the train car. Okay, reason being that if this person wants to measure the length of the train car, they just go, oh, no problem, I'm going to shine a light this way, it's going to hit a mirror at the end, come back, and it's going to hit me simultaneously, right? And I'm going to measure, and in fact, it's like, well, I can set my middle of the train car by checking the difference in time between me receiving these light beams back. So if I put mirrors at the two ends of the car and I shine a light at the exact same time, right? I have a double-ended laser, goes that way. If I'm over here a little bit, then it goes, and I go, oh, this one took longer, I need to move this way. And now it goes, oh, got it, this is the center. Okay. Now, if that person's doing that, can you see that this person's going to disagree that that's happening? Right? In other words, what this person's going to see as the train car moves this way is that if the light leaves here simultaneously, this one's going to have to travel a lot further than this one, right? And they're not going to come back and hit simultaneously. So the idea being now that as this person says, yes, I can measure the actual length of the train car, this person's saying, well, I don't agree with that. On the other side of things, this person's saying, look, I should be able to measure between the two lightning strikes. This person's saying, no, that's not at all true. You're not measuring properly between the two lightning strikes. So again, we run into this situation of what's going on. So what's going on is, yes, this person should be able to measure the proper length of the car. Okay, this person should be able to measure the proper length of the car because that person can actually measure the two ends of the train car simultaneously. They are at rest with respect to the train car. Therefore, they should be able to go, oh yeah, here and here. This person is not at rest with respect to the train car, and so this person will in fact measure a shortened train car length. So let's talk about what happens here. I had that thing down here. Well, you would say that the length of the train car as measured by someone on Earth, right? So this would be length of the train car as measured by Earth is length of the train car as measured by someone on the train divided by the gamma factor. In other words, this person measures the proper length of the train, and that is the literal word for it. It's the proper length of the train car. This person measures a contracted length of the train car, and that is because the train car is in motion with respect to the Earth observer. Okay, so the tagline here is that moving objects are contracted in the direction of their travel. And that's important, because what that tells you is that if I have something like this moving this way, you will see still a 1 meter height. As long as it's moving horizontally, you'll still see a 1 meter height, but it will be thinner. It's going to be contracted only in the direction of the motion, not like it's going to get squashed this way. It's not. If it's moving that way, it gets squashed this way. Not squashed, but it appears to be contracted. Are contracted along their direction of travel. Okay, so again, this is something that you have to be careful with, all right? And the reason for that is because it depends on the viewpoint that you take, okay? Remember that relativity is about trying to answer the question, what does it look like from that person's frame? That means you have to throw yourself into that person's frame mentally and look around and see what is going on and think about what does it look like from their perspective. Their origin is here. Things are moving differently with respect to them. Okay. So the idea of Earth always being the contracted length measurer is not going to be the case. The train always being the proper length is not going to be the case. You have to make sure that you're applying this. What's moving with respect to what? Okay, so it's the same idea with the clocks. Now, we did an example last time where I was taking a trip to Andromeda, and I told you that the distance to Andromeda is 2 million light years. Okay, but if I'm saying that Earth and Andromeda are separated by 2 million light years, that's like me being on the train and looking at, well, Earth is here and Andromeda is here, and I just got to stretch a tape measure between them. Granted, it's a long tape measure. Okay, but it's there, boom. I can take simultaneous measurements. Now, a rocket ship blasts off and comes flying past, right, and is taking a trip from Earth to Andromeda. What is it that they see? Okay, now they're in the quote-unquote moving reference frame. Well, no, because we're going to jump onto the rocket ship. We aren't moving. What is moving? Earth is heading back that way, and Andromeda is approaching me. So I see the distance between Earth and Andromeda to be shortened because they are moving with respect to me on the rocket ship. See what I'm talking about here? It's not always this way with the subscripts, but it is this way. And this is the thing you have to concentrate on. You have to put yourself in the other person's perspective and realize what it is that's moving. Okay? So careful with stuff like this. All right? And the same thing was true with the clocks, right? The same thing was true with the clocks. When I was on Earth and I watched the rocket go by, I saw that the rocket had dilated time. The rocket had longer time. The watch wasn't clicking as fast on the rocket as it goes by me, right? So there's a disconnect. I don't know. That's not the right word, but there's a schism between these two lengths and times. In other words, if I think of who measures the proper time and the proper lengths of things, they're always different people. Because the person on the rocket, right? The person on the rocket is going to look at the time and go, the clock's not moving. I'm keeping time on my watch and this clock's not moving. Therefore, this is the correct time of the journey, right? The person on the rocket traveling between Earth and Andromeda will look at their watch and see that clock has not moved in space because Earth and Andromeda have gone that way, and therefore that time is the actual time of the journey. But they're not going to measure the proper length between the two endpoints. Whereas here on Earth, I'm going to measure the proper length between the two endpoints, but I'm not going to measure the correct time because I'm going to look at the time and it's going to be wrong because it's, right? I'm going to have to look at my watch over here and then that watch, which is way over there, and it's moved with respect to me. So it hasn't told me the right time. Therefore, the correct proper time is the actual word for it. The proper time and the proper length are measured in different frames. Okay. In that example, the proper length was measured by the Earth observer. Earth to Andromeda is the proper length. But the time of the journey, proper time, is measured by the person on the rocket. So it's, like I said, it's a kind of a shift. It's a bit of a paradigm shift here. Okay, so we've talked about times and we've talked about distances. So the moving clocks are running slower. The Earth clocks are, if you like, not running slower. Let's talk about the paradox of the twins. I think I left off with this last time, but my memory is not what it used to be. So just in case I didn't, imagine two people born at the same time here on Earth. They grow up, they're 20 years old. One leaves in a rocket ship and visits a faraway planet, but decides not to stay, turns around immediately and comes back. So first of all, let's draw this on the space-time diagram. I'd really like to use this one, but it doesn't look like I'm going to be able to. I need something larger than that. So we're going to go here, and we're going to draw this again. And we're going to try and make sense of the twin paradox. All right. I'm going to use a nice large set of axes here. Okay. Here is the set of axes describing the Earth twin. And the rocket twin blasts off and goes along the journey. So the light line would be here. Okay, the light line would be there. I can't go past that for my t-axis. So I'm going to incline it something like, say, here. All right, we'll call this the t prime axis. This is the axis of the person on the rocket ship. Okay, so here's the x prime axis for the person on the rocket ship. It should be somewhere about like there. Oops, come on, pen. I'm trying to darken that in so you can see it. Here's the x prime axis. That's the person on the rocket ship's space axis. All right, so what do we see? Well, what we notice is that, first of all, the Earth observer sees the rocket clock going past and says, your clock's running slow. The person on the rocket sees Earth going by and says, your clock's running slow. So the question is, who's right? Because this will happen both on the outbound journey and on the return journey. Okay, it's relative motion. As long as they are moving relative to one another, they're going to see, oh, that's a moving clock. Whether it's going this way or going this way, it doesn't matter. It's the fact that the clock is in motion with respect to the Earth observer. So the Earth observer says, oh, okay, there's a rocket ship going that way. That clock's running slow. The rocket turns around, comes back. Oh, your clock's still running slow, right? And so the rocket observer does the same exact thing. Says Earth goes away, clock's going slow. Earth comes back, clock's going slow. how can two people then meet back up and disagree whose clock went slower? This is the paradox, yes? In other words, if I say I'm on Earth and I say the rocket clock was slow the entire time, you should be younger than me. But the rocket person says, no, no, you were in motion with respect to me the whole time. Your clock should be slower. That means you should be younger. How can they both be younger than the other one? Right? There can't be two outcomes to this. They have to ultimately agree. So we have to resolve this. And so we will, I guess. Let's suppose that the rocket reaches the planet, here? I don't know if I'm going to manage it if I do that. I can barely manage it. Okay, right there. There's the planet that the person reaches, and then here's the return journey. It's going to go up like this. It's going upstairs pretty high like that, but I am going to barely manage it on the end of the board right there. It's going to go up. Okay, so they meet again way up here, the very top. I guess I should have put this down here. Oh well. Here's the planet. And so you'll notice that the rocket observer spends 0 time at the planet. It's a rather unphysical kink in the world line of the rocket observer. In other words, going this way to then going this way in 0 time. Okay. So this is what we would call the kind of worst case scenario, because that acceleration is so much. Anything that would engender some type of turnaround will be less than what we're talking about. Now, notice, here's what we're going to do. I'm going to look at the rocket's journey from Earth. First, Earth is along this line. I'm standing here on Earth and I'm going up, and I experience some length of time, which is the entire length of this axis here. Okay, that means that the rocket hit the planet right here, according to me, on Earth, and that's the halfway time. Okay, so the Earth observer notices that the rocket reaches the planet at that time. This is the simultaneous measurement thing, right? Now, right at that time, say, as the rocket is getting really close to the planet and notices the planet and is like, oh my gosh, I have to turn around. Let's put ourselves on the rocket at that point, okay? Well, actually, let's put ourselves on the rocket the entire time. Earth's going this way, we're noticing the clock. Clock's running slow. Slow, 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 slow. Right when I'm on the rocket ship and I'm about to turn around, I look back and I see what is Earth's clock right now. In other words, I, in the rocket, want to make a simultaneous measurement of Earth's time as I'm turning the rocket ship around. Okay? Now this is where things get a little bit questionable, but mathematically, right? I know the time to turn around is 0, but let's go slightly prior to that. And I'm going to, right before I turn around, I'm going to look back and look at Earth's clock, right before I turn around. That means I'm simultaneously measuring the time on Earth with my beginning of the turnaround. That is therefore something that is parallel with my space axis. I am on the rocket, that's my space axis. Therefore, the time on Earth when the rocket turns around is this, is here. Is that one right there. That is the time on Earth as seen by the rocket as the rocket begins the turnaround. In other words, I think you can see that we're already disagreeing on time. The Earth observer is saying the time is this much on Earth. The rocket observer is saying, no, time is this much on Earth. That's how you see that the time has gone slower on Earth from the rocket frame, right? There's a difference here, and that's the slowness of the time, okay? So the way that you see that the rocket has slower time from Earth is not quite so easy, but it's in how the hash marks, how you count time on the time prime axis here, on the t prime axis. How do you count time? It turns out that the hash marks are larger. So if you think of this as being 1 year, 2 years, 3 years, 4 years here on Earth, that would be 5, 6. So here on Earth, we would have said the rocket turned around at 6 years. The rocket is going to say, no, when I turned around, your clock was reading 4.5 years. You are not reading the right? So that's how the rocket person is going to see Earth is running slow. Earth's time is running slow. How is the Earth observer seeing the rocket observer's time running slower? So what's happening is these hash marks are counted differently. In other words, the 1, 2, 3, 4 marks are spread more in that way. So here on the rocket ship, that would be 1, that would be 2, and so that would be 3. Okay, so the way I have it, the Earth observer would look at the rocket clock and see your time on the rocket at turnaround is 3, my time is 6. I should have made it symmetric. It should be 4.5 because it should be symmetric both ways. So I didn't do very well here. I should go back and correct that. Okay, I'm not happy with the way I did this. Okay, sorry. We're gonna have to do this again. I'm gonna have to shorten these down. So I'm gonna go 1, 2, 3, 4 and a bit. All right. So what did I just do? 1, 2, 3, 4 and a bit. Okay, that's more realistic because they should be equal, right? They should be seeing the same amount of no, that's wrong, isn't it? Because that implies that the person, okay, sorry, I'm having a little bit of, see, you think this stuff's easy? It's not. Even I mess it up. So hold on, I was right the first time. I have to see no, I'm fine. This is fine. I have to look at my clock. Actually, it should be even more than this. Because if they're looking back seeing 4.5 years on the Earth clock, that should be slow according to their clock. Okay, now I'm getting it, right? Now I'm getting it. So let's put, I'm trying to make these dang hash marks right and I never, okay, so let's put 5. 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5, and a little bit. Okay, there we go. I'll get there one of these days. Trying to make it good. The point is that the hash marks along the t prime axis are not spaced the same amount as they are on the t axis. Okay, so where the Earth observer would see 6 years, they would look at the rocket clock and see 4.5 years, but the rocket clock would look at its clock and see 6 years, and it would look back at the Earth clock and see 4.5 years. Okay. So the question then is, on the inbound journey, let's look at what happens. Now we've looked at the rocket, which was just about to turn around. Let's look at what does the rocket see right as it turns around and is now headed back towards Earth. That is simultaneous with the turnaround, which means that I have to think about the axis, the space axis, which goes along with this time axis, world line of the rocket ship, right? So if I look at that, I would have to say that the space axis to that is this. Let's see, is that going to be true? No, it's going to be more like this. There it is. Okay, so it's going to be here. It's going to be more here. So the space axis to that would be this one. Call that the x double prime axis. And therefore, what I would see as I turns the rocket ship around is that this is the time that is now on Earth's clocks. This is time on Earth when the rocket begins back, and when the distance between rocket and Earth starts to shorten. So this is start of the return. The start of the return journey. Therefore, the person on the rocket then sees again contracted time on Earth, and again the person on Earth sees contracted time on the rocket. So everything is totally symmetric in those two cases. But notice what happened during the turnaround. During the turnaround, which is this, from this black dashed line to this blue dashed line, during that time, Earth's clock jumped from, say, this 4.5 years to this up here, which takes another 4.5 years to come back. So something strange happens. And during that quick turnaround, the rocket observes Earth time going really quickly. Suddenly, it jumps from here to there. It's almost as if you imagined like a sped up, like many of you probably watch me on double speed. It's the same exact thing, except way faster, right? So you see a whole bunch of stuff from Earth reaching you at the same time. And then you've basically jumped into Earth's future as the rocket observer, right? You were here, and now you turned around and you jumped up to here, which means you jumped further into the future without experiencing any of that. Therefore, you as the rocket observer are the younger one. And the Earth observer is definitely the older one, and it's because of that jump. Furthermore, you can distinguish between the two observers because you know who made the jump. As soon as this turnaround happens, what you're going to see is there had to have been something that turned the rocket around. In other words, there were forces exerted on the rocket to slow the rocket down, bring it to a halt, turn it around, speed it up that way. Earth didn't experience any of that stuff, right? There were engines firing, there was forces exerted, there were things going, right? You can tell when a frame is getting accelerated. But Earth's frame never experienced any of that. Therefore, the person who had the jump in the time is the person who experienced all the forces and accelerations that caused the jump. And in this case, therefore, that was the rocket twin. The rocket twin, therefore, is the one that comes back younger. And because of that, both Earth and the rocket twin agree on this. And you can set this up even from Earth's perspective. I won't go into the whole thing, but there are ways to do this. You can imagine firing light pulses out, one per year or something from Earth. And you can count how many you send out from Earth and how many the rocket receives. And you can calculate the amount of time between each of those pulses, and you'll see that the time on the rocket is less than the time on Earth. And it's going to work out that way. Therefore, in this case, it's because of the turnaround. The turnaround implies acceleration. And that is what kinks the world line of the rocket, which causes the rocket to experience a jump into the future of the Earth frame. Essentially, this turnaround causes a jump into the future. Where it didn't jump into its own future, it just jumped into Earth's future. And therefore, it's the the Earth, the rocket twin, therefore, rocket twin comes out younger. All right, and that's the resolution to this rather strange paradox. Many of these types of paradoxes have been proposed to contradict the results of either special relativity or general relativity. And by the way, if you want a full analysis of this situation, it really is a GR problem. Why? Because this turnaround is not constant motion in one direction. So it doesn't really fall under the auspices of special relativity. It does, however, indicate accelerated motion, and that's a GR scenario. Okay, so you can also analyze this from the general relativistic perspective, and you will still find the same thing. A lot of these paradoxes, which were designed to show flaws and inconsistencies in both SR and GR, have all turned out to fail. There hasn't been a successful conclusion or a successful upholding of a paradox that causes someone to say, oh, look, GR is incorrect. So it's been 120 years since special relativity. It's been 110-ish, 111, I don't know, since GR. And we're still finding results from these things. I will also say that there is, I mentioned this last time, that there's experimental evidence for each one of these, both SR and GR. And it just mounts up by the day. In fact, to the point where somebody put a really precise clock in an airplane and flew it around in relative motion with respect to Earth for a whole bunch of time, came back down, measured the differences in the clocks, and it was exactly what was predicted. So there you go. Even to the point where we have to reset clocks on the satellites because they are in motion. The GPS satellites are in motion with respect to us, and therefore we have to reset their clocks ever so slightly every, I don't know, whatever, I don't know how often they do it, but it will drift because the clock will drift off Earth time because of its relative motion, and also because it's higher up in a gravitational field and things like that. But nonetheless, the clocks are different, and everything we do in order to reset them works. They're off by exactly how much we think they should be according to the relativity theories. So apparently these are reasonable, at least for now, until someone comes along and shows us how they're all wrong. Pretty cool. Okay, we have that. I want to go into a little bit more of dynamics at this point and just finish, or actually start a few things which I can finish tomorrow on the dynamics. And what that means is I want to examine the issue that I brought up last time about momentum, or the other time about momentum. The momentum as defined by Newton's laws has to be wrong, right? I was telling you about momentum and I was telling you how, hey, wait a second, we can't really go along with Newton's second law because a constant force produces the same change in momentum, and if it's a constant mass object, it should produce the same change in velocity. But that can't be right, okay? That can't be true somehow. So what is Newton's second law telling us? Well, what it's telling us is that we have to redefine what momentum is. Because momentum can't just increase such that V is greater than C, right? V can't increase past C. It has to stop at C, according to relativity. And again, we have no reason to disbelieve it. So we have to figure out what we can do to the momentum to cause it to be a relativistically correct quantity. So what we do is we say, okay, well, the vector sign doesn't really matter because it's just 1D, so I'm just going to take that away. What we're going to do is we're going to say, instead of being mv, we're going to put the gamma factor in there. Because now the momentum can still increase as it should without causing an increase in v or m. All right? That's because as you go faster and faster, the gamma factor gets astronomically large as you get closer and closer to c. And therefore, this gets to be really big. And that means that you can't go past c, because when c is 1, when v is c, right? In other words, v is 1, then this quantity is essentially infinity. If you remember, where gamma is equal to 1 over the square root of 1 minus v squared, if v is 1, then this quantity is infinity. As we approach 1, that quantity gets to blow up very closer and closer up to infinity, which is telling us then that, okay, we now have a way of preventing the momentum from growing ever bigger in a finite way. It's already way too big, and I can't go past c. I can't get my v to be past 1. Now, you might say, okay, that's all well and good. You can actually go back into Newton's laws and how the derivatives were taken and realize that the derivatives have to be taken a little bit differently. And that's where the gamma comes in, because those derivatives were with respect to time. If you remember Newton's second law involves d by dt of the momentum. Well, whose t is that? Asks relativity at this point, right? In order for this to be correct, we have to make it the proper time. That's where the gamma comes from, okay? So the gamma is in there not to say that the mass is increasing or something ridiculous like that. And I will tell you this is a lot of textbooks, a lot of places will say, oh, you can't go faster than c because if you push, then all the momentum goes into making the mass bigger. But that's not really true. That's not, the mass is not getting bigger. The momentum is getting bigger than what we classically would have expected it to be because we defined it wrong in the first place. We didn't know that, and that's fine, but that's what it's supposed to be. All right? So you will find textbooks and other places out on the internet saying because mass gets larger. Mass doesn't get larger. Mass stays exactly as it is. It's the definition of momentum that was not correct. So just to let you know, you will see stuff like that. In this case, then, what we're going to do is we're going to define an invariant. We had the interval last time was our invariant. We had remember we had s squared being t squared minus x squared, right? That was a kinematic interval such that we could define the distance between two spacetime points. Well, now I'm interested in seeing what's the invariant when I'm talking about energy and momentum. The invariant, okay? And here's why I'm telling you that the mass is not increasing. The invariant is the mass because one of the main tenets of relativity is that there's no experiment you can do, I should say of special relativity, is that there's no experiment you can do to deduce that you are in motion. As long as it's constant motion in a straight line, right? As long as you are a Newton's first law observer, there's no experiment you can do to say, I'm in motion and you're not, right? Now, we all, quote unquote, know that when we drive a car, we drive, right? We're the ones moving around on Earth. We all kind of know this from an intellectual standpoint. But the laws tell us that, and by the way, we don't experience constant motion in a straight line very much because cars bounce and, there's turns and accelerations and things like that. So Galileo was the first one to think of this, or I don't know if he was, but he was the first one to put forth this argument. Suppose you were in the hull of a ship, no windows, and you're on very still water, such that there's a slight wind blowing that's just enough to overcome the water drag around the ship's hull. So the ship is moving very slowly at constant speed along one direction. There's no significant wave motion or anything. So you are in the hull of the ship. You can't see outside. Can you deduce if you're in motion? The answer is no. So you can do all sorts of things like toss the pen up and down, and it always returns to my hand. I could time how much it takes for something to drop to the floor. That would be exactly the same as if I was standing still on Earth. All of these experiments give the exact same results as someone who is at rest on Earth. So, getting back to this, the mass of something doesn't increase just because it's moving. So what we define as an invariant is the rest mass of an object. The mass of right? If I was moving and I could get on a scale and go, oh look, now all of a sudden I'm 395 pounds. Oh, I'm in motion. That would contradict all of the ideas of the mentalities behind physics. So I have to be able to step on a scale and go, I am the weight that I am when I'm at rest on Earth, and therefore, I can't tell if I'm in motion or not. It seems like I'm at rest. Okay, the invariant therefore is the rest mass. And the rest mass we define in exactly the same way as we defined the interval. We say it's m squared, except now instead of t and x, we're going to use the energy squared and the momentum squared. Now, remember, I have set c equal to 1 in these things. So if I were to make it such that c was not 1 and I wanted to see the c, it would look like this. Like that. Such that when we look at the rest mass of something, right? If something's at rest, it has zero momentum in its reference frame. Therefore, the momentum is zero. And lo and behold, we get the idea that E is equal to mc squared. And this is, of course, probably the most famous equation in all of physics. And so it's nice to be able to say, hey, by the way, we're dealing with this, and it's available for us. We've got there. We're thinking about energy and mass now as the same thing. And that's another shift in thinking where chemistry teaches us that mass is constant, right? This is kind of where we come, and this is how we arrive at that mentality, is generally through chemistry, and also just the idea that, well, if I take this pen and I break it in half and I measure the masses of the two, of course I should get the mass of the whole pen. Yeah. Well, not always, okay? And so this spawned a great amount of very interesting physics, and I think that is what we will pick up with when we start class next time. And I will bid you happy rest of your day. Don't forget to start, oops, I erased it, on homework 6. Homework 6 is up and ready to go. There's some space-time diagrams in there for you to look at. There's a couple of calculations to peruse on. There's some calculations involving the gamma factor. So have a bit of fun. It's pretty light, shouldn't cause too much consternation, but just make sure you're in the mindset of trying to remember who's doing what in what frame. With that being said, have a great rest of your day, and I will see you next time.